So another technique to assess the performance of a model is called cross-validation. Cross-validation is a technique in machine learning used to evaluate the performance of a model, where we divide the data set into subsets and using one subset for training and another one for testing. So why do we use cross-validation? So cross-validation can be used for two reasons, right? So first of all, it helps to reduce, so this one helps to reduce something called overfitting. Okay, so it helps to reduce overfitting. Okay, this is a big problem in machine learning. Okay, and then of course, once we reduce overfitting, it helps to provide a better estimate of the model generalization, right? Where the model, we want to assess the model's performance on unseen data. Second of all, cross-validation can help identify optimal hyperparameters. Okay, so we want to find optimal hyperparameters. So for example here, actually for the model, so different hyperparameters can lead to different performance on different k-folds, right? So let's look at how cross-validation works. So cross-validation here works in the following, right? So the first thing, we want to divide the data set. So assuming this is our data set, right? We want to divide the data set into k equal partition. This k equal partition, we call them k folds or folds. Okay, so we call this folds. So 1, 2, 3, 4, 5. So for example here, our k equals to 5. Okay, so the second thing is that each fold, each of these fold, we consider it as a test set and use the k-1 fold as the training set. So in this case, we have 1, 2, 3, 4, 5, right? For a training set, this would be k-1. And now k here is 5. So 5 minus 1. So these 4 partitions or folds will be used for training. And then the shaded region here, the blue shaded region here will be used as our test set. Now, we train our model on this k-1, all right? And then we use it to assess the performance of this model on this test set, okay? Now, this process is repeated k times until each of these folds has an equal chance to be used as a test set, as you can see here, this diagonal. So by the time we iterate up to the 5th iteration, each of these folds has an equal chance to be used as a test set, okay? So each time we do this, we record the performance. So let's say this performance 1, performance 2, performance 3, until we're done with the iteration. And then lastly here, we calculate the average performance of all these, processes or this iteration. Now we use this average performance as a benchmark to compare with other models. It's important to note that the choice of our k here will affect something called the bias variance trade-off. Okay, we're gonna look at this in another video. Okay, so a higher value of k, e.g., let's say we have k equals to 10, right? So a higher value here gives it will give lower variance, right? At the same time, it will also give high bias. Okay, so this is a phenomenon we call underfitting. So when a model has low variance and high bias, we say this is underfitting. Okay, that means this model is very simplistic. All right. While a smaller value, let's say k equals to 5 here, okay, this will lead to high variance, okay, high variance and low bias. Okay, so this phenomenon, we call this overfitting. So this is a concept called overfitting. All right. So the goal here, we want to find an optimal k that that depends on the size of the data set. Okay, this optimal value, will help us find the trade-off between bias and variance. Okay. So let's quickly look at an example here. Suppose we have a data set that has 1,000 samples, right? So what we do here, let's say k equals to 10. So k equals to 10, right? Or maybe in our case here, we can just, say equals to 5 because our diagram here has 5. So we can just say k equals to 5 here, all right? So each fold of this, so each of this fold will have 200 samples, right? So each of this fold will have 200 samples, all right? So the total samples here should be equals to 1,000, all right? 1,000, okay? So the first fold, you know, it will be left as a test set, okay? And then the remaining, which will be K minus 1, which is 4, is gonna be used. So this is gonna be used as the training set, okay? So this 4 will be used as a training set. So essentially here, we're gonna train our model. This training set will have 800. Essentially, this is just 200 times 4, okay? So we train our model on these 800 samples, then we get the performance of that and we test it on this test set. Okay, this test set, remember, has 200 because each fold here has 200 sample, right? So we train our classifier and evaluate on this test set, all right? And then we repeat this K iteration, we'll repeat this 5 times, okay? So like this. So each time we calculate the performance and record that performance 1, performance 2, performance 3, 4, 5, 6, up to 5, right? Then we average this performance, okay? And then we use this to select the best performing model or algorithm based on this average metrics, okay? All right, so this way we can ensure that the model's performance is evaluated on a diverse set of samples, okay? Not just a single set. Okay, which can give us an overly optimistic or pessimistic estimate of a model's generalization performance. And then lastly here, we also have other types of cross-validation. We've already talked about K-fold cross-validation. We also have stratified K-fold validation, where the samples are divided into K-folds such that each fold has approximately the same proportion of class labels, all right? Again, it's very useful, especially when you're dealing with an imbalanced data set. So leave one out cross-validation. This is a special K of K-fold CV, where K is equals to the number of samples in the data set, okay? Now, this is the most comprehensive type of cross-validation, right? However, it's very computationally expensive. So just keep that in mind. Then the holdout method, this is the simplest technique where we divide the data set into 2 parts, one called training set and another one called test set, okay? So again here, this is a very quick and simple way to evaluate your model. You'll see this a lot when you're training your classifier. Of course, again, this will lead to high variance and can be very optimistic. And then lastly here, we have shuffle split cross-validation. Again, this is a technique where we divide the training set and the test set multiple times, okay? So the size of this test set can be specified, and the data is shuffled before each split, all right? So the choice of the technique depends on the size of the data set, all right, or the type of the problem and the computational resources available, okay? All right, and that's cross-validation.